Good afternoon, everybody. My name is Ray Volkas, and I'm the chair of the neutrino session. So we're going to have 4 talks, 3 experimental and 1 theory. The duration of each is 30 minutes, and we'll aim for 25 minutes for the talk and 5 minutes of questions, and we'll see how we go. So the first speaker is Masashi Yokoyama, and he will review long baseline experiments.
Okay, thank you. So I'm going to talk about the long baseline neutrino experiments. So, including the accelerator long baseline and some reactor neutrino experiments. So the main topic of my talk is about the neutrino oscillations. So neutrinos are produced in the weak interaction and also detected again in the neutron interaction, weak interaction. And but in between, when they propagate, they are in the mass eigenstate, and then the weak eigenstates and the mass eigenstates are not identical. Actually, they are connected with a unitary matrix, so-called PMNS matrix. Then the this mismatch induces that flavor change during flight. That's called a neutron oscillation. And in the simplified case of the 2 flavor, neutron oscillation probability can be written like this. And that's dependent on the mixing angle, that's content of this mixing matrix, and also the delta m square, that's the mass square difference, and the flight length and energy of neutrinos. So because delta m square is typically very small, then we need a long length to observe this neutron oscillation phenomena. So this is a super macroscopic quantum effect we can observe. So the first firm discovery observation of this neutron oscillation was reported 20 years ago from Super Kameo Kande and in 1998. And since then, many experimental efforts brought us a lot of information about the properties of neutrinos. Still, we have many questions newly arising and remain unresolved, like origin of tiny mass, very tiny mass of the neutrinos. Actually, neutrino mass is much, much smaller, orders of magnitude smaller than other fermions. And also the large mixing matrix, that's totally different from the clock sector. And also mass hierarchy or mass ordering, that's which of 3 possible mass eigenstates are the heaviest. And also, is CP violated in the lepton sector, or is there any extra neutron families? And those properties of neutrinos are believed to be connected with fundamental big questions, like source of the baryon asymmetry of the universe, or physics at a very high energy scale through like a seesaw mechanism, or origin of generations in the fermions. So thanks to the great effort from many, many experiments over 20 years or more, now we have fairly good measurements of oscillation parameters like this. Oops, sorry. So we have 3 mixing angles and 2 independent mass square difference, and 1 complex phase that's the source of the possible CP variation. And so although we have some measurements on those parameters, but its precision is getting better and better, but still not as good as corresponding clock sector measurements. So we would like to more precisely measure those parameters to understand the fundamental physics behind the flavor structure. And also, we want to search for the CP violation in the lepton sector and determine mass hierarchy, and also octant of theta 2-3. Theta 2-3 is known to be very close to the 45 degree, which is a kind of the special angle, which is called the maximum mixing. So if theta 2-3 is less or equal or greater than 45 degree, will give us some hint to the possible flavor structure or symmetry behind the mixing matrix. So those are our main targets of the current neutron oscillation measurements. So let me start from the reactor measurements on the theta 1,3. So from reactor, we have many anti-electron neutrinos, new bars, and using this new bars disappearance measurement at the baseline of order 1 kilometer, we can have almost pure measurement of sine square to theta 1,3. This is the oscillation probability, and this term is negligible at the baseline of 1 kilometer. So almost pure measurement of this theta 1,3 is possible. And new bar from reactor can be purely and efficiently detected by using inverse beta decay, which cross-section is precisely known with a delayed coincidence to suppress the background. And by putting two sets of detector, one at the near side where oscillation effect is small, and the other at far detector side where the oscillation probability is near maximum, and comparing measurements of those two almost identical detectors, we can control systematics to the less than 1% or even 0.1% level to enable the precise measurements. And there are three reactor theta 1,3 experiments. One in Diabé in China, second one is Dabusho in France, and the third one is Renault in this country, South Korea. And they are all basically the same principle shown in the previous page, but have some variations of parameters like reactor power or baseline or detector mass. But all three experiments provide precise measurements of theta 1,3. So this is latest results reported in this iChip, and Diabé, Dabusho, and Renault all provided precision measurements of the theta 1,3 down to 5% or better. And also, they provide measurements of delta M square using the Neubauer disappearance. This is, actually very good measurement, and the value is consistent with a new measurement of new disappearance from the accelerator and beam experiments. And also, precision is actually comparable to those with other measurements of the new disappearance. And from those reactor experiments, also there are reports of the other measurements like neutrino flux or spectrum or reactor Fourier composition, but that we will cover actually in the later talk. And all three experiments plan to further improve the measurement by more data and analysis improvements, so we can expect more precise measurements of the theta 1,3 from all three experiments. Beyond that, next large reactor experiment, neutrino experiment, this is not for the theta 1,3, but the other physics, but 20 kiloton Juno will be 20 kiloton liquid scintillator detector, at around 50 kilometers from the reactors. And with this baseline, this is a maximum at the atmospheric delta M square scale. Juno will aim to determine the mass hierarchy and also provide other many measurements, most notably precision measurements down to sub-percent level of those oscillation parameters, and also other rich physics using reactor and other sources of neutrinos. And civil construction is ongoing, and also detector R&D and fabrication are in progress, and there are several reports in this iChip, and they aim to start data taking in 2021. So switching to the accelerator-based neutrino experiments. So in accelerator, we can produce intense muon neutrino beam by hitting target by the high-energy proton beam that produces many pions. And then pions are focused with magnetic horns and decays into the muon neutrino. That's a muon neutrino beam we can utilize. And we sample this neutrino beam with a near detector and far detector several hundred kilometers away to measure the neutrino oscillation. So using measurements from the beam monitors in situ, and using hadron production cross-section measurements, like NA61 at CERN, we can predict the neutron flux and uncertainties, and also their correlation. And then this flux and neutron interaction cross-section is constrained using the near detector measurements and with the help of the cross-section measurements at models. And altogether, this near detector constraint flux and cross-section and their correlation. And this information is extrapolated to the far detector using some correlation matrix to make a prediction at the far detector. And then this prediction at far detector is compared to the observation at far detector to extract the oscillation parameters. So this is a principle of the long baseline experiment. And because we use a muon neutrino beam, there are two possible measurement channels in the long baseline experiment. One is the new mu disappearance, where we measure the survival probability of muon neutrino, which is sensitive to the sine square to theta to 3. And the other is the new appearance, and this is a appearance probability. And the leading term is sensitive to the sine square to theta 1, 3. That is the same angle as the reactor experiments are measuring. But through the sub-leading terms, also this new appearance is sensitive to the effect from the complex phase that possibly violates CP in lepton sector, and also the matter effect that will bring us information on the mass hierarchy. So using both new disappearance and new appearance, we can measure those variety of the oscillation parameters. So recently, couple of experiments reported final results. One is the MINOS plus in the United States using a Fermi-Lab neutron beam to the Sudan, 730 kilometers away. And they, based on the 12 years of data, they provided precise measurement of theta 2, 3 and the delta m square. And moreover, combining MINOS and MINOS plus had a higher energy beam, and they provide a new mu survival probability over a wide range of the neutron energy that was found to be very consistent with the prediction from three flavor framework that put tight constraint on the exotic scenario, like extra or even large extra dimensions. So the other experiment, OPERA, also reported final results from their tau neutron appearance search. And OPERA is, used a beam from CERN with a huge immersion-based tracker located in the Gran Sasso. And they observed 10 new tau event candidates in their final dataset over 2 backgrounds. So they confirmed appearance of tau neutrino from new muon neutron beam with a 6.1 sigma significance. So, and currently ongoing long baseline neutrino experiments are T2K and NOVA. T2K is an experiment in Japan using intense neutron beam from JPAC accelerator located in Tokai village, and the Super Kamioka, big water Cherenkov detector located in Kamioka as a far detector. And the baseline length is about 300 kilometers. NOVA uses a Fermi-Lab neutron beam to far detector located in Ash River, about 800 kilometers away. And T2K and NOVA have different baselines, meaning they see a different effect from the matter effect because of this different baselines. And T2K has shorter baseline, meaning less matter effect and purer effect of the CP violation, while NOVA has a longer baseline that with more matter effect and more sensitivity to the mass hierarchy. Actually, combining those two experiments, we can infer more information. So those two experiments are very complementary. And in this conference, T2K reported new results based on the more data, especially anti-neutral data is 50% increased compared to last year's result. Actually, last year, T2K increased twice neutrino data compared to the 2 years ago. And NOVA reported fast analysis, including their anti-neutrino beam data. So yeah, we have very brand new results in this conference, I checked. And I'll start from the T2K. So T2K is a super Kamiokande water channel detector. So in T2K, neutrino events are observed through this Cherenkov ring pattern in the water Cherenkov detector. And from the ring pattern, we can identify muon-like candidate and electron-like candidate that's corresponding to interaction with nu mu and nu e. And also, we can reconstruct the energy and the direction of the final state leptons, from which we can infer the energy of the neutrino. And from last year, T2K applied an improved reconstruction algorithm in the super K data, which uses the maximum information from all the PMT of the charge and time information into a likelihood and extracts the particular kinematics and ID information from the PMT hit information. So this brings T2K an improved signal efficiency and purity, and also by re-optimizing the fiducial volume cut, effectively statistics was increased by about 20% with this new algorithm. And also T2K employed many improvements in the cross-section modeling to improve the analysis. So this is T2K data up to the end of the last year. And this is nu mu bar, nu e, and nu e bar. And for the electron neutron sample, T2K uses some additional sample with a single pi plus production, where pi plus is tagged with associated decay electron signal in the super K to increase the statistics. And this number shows that statistics of events. And this is a reconstructed neutron energy. And in electron case, the two-dimensional information of the reconstructed energy and the scattered angle of the lepton. So using these 5 samples altogether, T2K extracts the oscillation parameters. And here is the result on the delta m square and theta 2-3. So T2K data is consistent with maximum mixing of theta 2-3. And these are parameters obtained. And also in T2K, Bayesian analysis was employed to get the posterior probabilities or assumptions of mass hierarchy and the theta 2-3 octant. And for mass hierarchy, T2K data weakly slightly prefers that normal hierarchy with this Bayes factor. Also in T2K, dedicated nu bar appearance search was performed by using the nu bar event sample. And the observed number of events are 9 events. Actually, this is less than what we expect from the oscillation parameter derived from other 4 samples than the excluding the nu bar. But yeah, using this number of events and momentum and angle information, we construct the delta chi-square and obtain this kind of p-value, these values of the p-values. And yeah, this time from T2K data, no strong conclusion was found. So we need more data in T2K to observe this nu bar appearance. Next is, yeah, this is theta 1-3 and delta CP measurements from T2K. And this is a sine squared theta 1-3 and delta CP Cantor. This is for with T2K data alone. So actually, with T2K data only, we can constrain the delta CP. And theta 1-3 is consistent with the reactor measurement. And with using reactor measurement measured value of theta 1-3 as constraint, we can get a tighter constraint on the delta CP. And this is a one-dimensional negative logarithmic plot for the delta CP with a different mass hierarchy hypothesis. And this vertical line shows a 2 sigma confidence level region from the T2K data with a reactor constraint. And as you see, the delta equals 0 and plus minus pi, where the CP is conserved, is outside of this 2 sigma confidence level region. So this is first hint of the CP violation in the lepton sector. Actually, the best fit value is near a maximum CP violation in the T2K. So NOVA is using, actually, NOVA has been pioneering the use of the deep learning technique in the event reconstruction and classification. And NOVA uses a convolutional neural network to classify events into nu mu, nu e, and neutral current. And their detector is segmented liquid scintillator tracking calorimeter. So treating each detector cell as a pixels, they use a technique in the image analysis and extract the feature from the events to classify those into those nu mu or nu e or neutral current. And for this round of analysis, they improve the classifier using the improved algorithm and improved input, also using a separate training for the neutrino and anti-neutrino data. And this is a NOVA data, latest data for nu mu, nu e, and nu mu bar, and nu e bar. And these anti-neutrino data are analyzed for the first time in this analysis. And most notably, this nu e bar, they observed 18 events over the about 5 expected background. So NOVA claims that more than 4 sigma evidence of nu e bar appearance with just first data set of the anti-neutrino data. This is a great achievement from NOVA. And this is a delta M square and theta to 3 from NOVA. And NOVA data actually prefer slightly non-maximal theta to 3 at 1.8 sigma, sorry, 1.8 sigma. And also slightly prefer upper octant at the similar level of significance. This is comparison of the delta M square and theta to 3 from various experiments. Red is TTK and blue is NOVA compared to the MINOS, ice cube, and super K. And they are all consistent and also consistent with maximum mixing at this point. So we are interested in looking for more data. And finally, this is a NOVA delta CP and mass hierarchy measurements. So this is a delta CP versus sine square to theta to 3 Kantawa is 1 to sigma for normal hierarchy and the inverted hierarchy case. And this is one-dimensional significance versus true delta CP. And there with assumptions of mass hierarchy and octant. And the best fit value is normal hierarchy upper octant, and delta is here. But for normal hierarchy, NOVA data shows some rather weak preference over delta CP. But for inverted hierarchy, this pi over 2 is excluded at greater than 3 sigma. And for mass hierarchy, NOVA data also prefer a normal hierarchy by 1.8 sigma. So this is a so-called by event rate plot. So horizontal axis is nu e candidate events, and the vertical axis is nu e bar candidate events for the TTK and NOVA. And those circles show the expectation of number of events in two-dimensional space for various oscillation parameters and the mass hierarchy assumption. And the TTK data is here. And so this is why this prefers maximum CP violation, while NOVA data is here. And this prefers upper octant, and the results shown in the previous page. So now both TTK and NOVA providing results with neutrino and anti-neutrino data. So we are at the very exciting time of the start of the investigating really CP violation in the lepton sector. Actually, both of T2K and NOVA has planned to further enhance their capabilities with beam power increase and reduction of the systematic uncertainty on top of the improvement of the analysis. So this is a CP evaluation sensitivity from T2K and the mass hierarchy sensitivity from NOVA. So both will reach around the 3 sigma, or around or over 3 sigma sensitivity in the end of the, by the end of the experiment. So we have very good prospects for the mass hierarchy or CP evaluation measurements in future. And beyond that, we of course have further next generation experiments, hypercameo current in Japan and doing in the United States, but this will be covered by a later talk in this afternoon, so I will not talk about this. And conclusions. So we have been seeing very rapid and steady progress in the neutron oscillation physics thanks to those experiments. And T2K, especially T2K and NOVA, started to explore CP evaluation and the mass hierarchy with neutrino and anti-neutrino beams. So this is a very exciting moment, and the excitement will continue with more results coming. So please stay tuned.
The next speaker will be Michele Weber, who is going to review short baseline experiments.
Okay, thank you to the organizer for having me here and giving this review on short baseline neutrino experiments. I made a little diagram trying to explain what we mean with short baseline. So if you start from the neutrino oscillation formula, which is a term with a mixing angle, there is also a term which has the difference in mass square and the propagation length over the energy. And so if you plot the length of propagation of the neutrino versus the energy, this is sort of slopes in this diagram, even though it's a log-log scale. So you can see we have experiments which operate with GeV neutrinos. There are experiments with MEV neutrinos. These are mostly reactor neutrinos or decay at rest. And these are accelerator-based neutrinos. And with different propagation length or baselines, we probe different parameters in these delta m squares. So for example, the about 10 to the minus 3 with thousands of kilometers of baselines, as we have just been hearing from the previous talk. If you go to MEV neutrinos, these will be seen at kilometer baselines. So, of course, on this plot, we now talk about short baselines. Shorter here means smaller slopes, and that means higher delta m squares. Of course, this is quite a simplification in this plot. There are 3 or 4, if you include stellar neutrinos. There are neutrinos and antineutrinos. There are experiments with appearance and disappearance, and there are also the mixing angles. But this should give an overview of what the short baselines mean. Also, if you go to shorter baselines, the rates of neutrinos that we see, or the flux, increases with 1 over L square. So at these experiments, at the shorter baselines, you can do measurements with high rates, high statistics of neutrinos, and measure cross-sections. So the 2 things that we'll be talking about are the sensitivity experiments to the high delta m squares. In particular, there are experiments with signs of additional neutrino with a delta m square around 1 eV square, and high statistics cross-section measurements. So the indications for more neutrinos than the standard 3 that we know of, I took on this slide from Yoming in a talk on Thursday, is an experiment called LSND, which measured oscillations from muon to electron neutrinos on the shorter baseline. The blue one here are the excess events that are seen here at lower energy, and they are only explainable with additional neutrinos in the eV square mass range. Also from Miniboon, which is an accelerator-based experiment at Fermilab, they have done measurements, and also here for neutrinos and antineutrinos, you can see here at the lower energy there is an excess of events over the background, which points to these additional neutrino states. There are also measurements done with sources or at reactors. The reactors will be covered by the next talk. What I will show here are updates from Miniboon and also new experiments trying to, or which will confirm or not the LSND measurements. All of these together, if you combine them, make combinations. Here's the delta mass square versus the mixing angles. In the combination, there appears to be possible areas around, as I said, delta m square, 1 eV square, which are still allowed for sterile neutrinos. So Miniboon has done an update. They have continued running, and they have doubled their data set on the neutrino side. So you can see here, again, the energy distribution of the events, the expected background events, and this excess here at the lower energy. If you just plot the difference to the expected events, that's shown here on the bottom, you can see here is the expected backgrounds, and this excess here amounts to about sensitivity of 4.5 sigmas. Also plotted are the events from the antineutrino data taking, which are at about 2.8 sigma combined. It's just short of 5 sigma sensitivity. You can also see the fits for possible 3+1 sterile neutrino events, which fit here more nicely in the antineutrino than in the neutrino. But from these fits, you can put allowed regions, again, in this plot of the delta m square versus the angle. As you see from the oscillation formula, you have these two sine square terms, and of course they are anti-correlated, so that's the slope down here. And then you have these regions. The blue ones are the data still from the LSND experiment, and these open areas here are shown are the allowed regions by Miniboon. The best fit happens to, in the newest data, to be here at the bottom right, but it's a quite shallow fit, so all these regions, in particular also around 1 eV square, is still allowed. The interesting thing is here that Miniboon in the continued running still confirms the signal in twice the data, so it was not a statistical fluctuation. It's still there in the data that have been taken, in particular at the same time as the short baseline program at Fermilab is running with liquid argon detectors. This is a picture that shows the beam is coming here for the left, Miniboon sitting here. Now there are 3 additional detectors based on the liquid argon technology that will be put on the same neutrino beam. Microboon has been taking data since about 3 years. So at the same time as Miniboon, that has just updated the results, there are 2 more. A refurbished and relocated Icarus detector will start next year, and the near detector SBND that will start around 2020. There are no results yet from Microboon. They are to come probably next year. There are more experiments. There is one experiment at JPark, JSNS square, which repeats the measurement of the LSND detector. So it's an experiment that is looking at anti-neutrinos, while the previous one was neutrinos, and looks at decay at rest produced neutrinos in a mercury target. So they look for appearance of anti-electron neutrino in this anti-muon neutrino source. I've taken the liberty to overlay a picture from the just installed vessel that they put there over the slide of Carson that he has shown on Thursday. And also they are putting the detector together and filling, and will start operation also next year. So let me just quickly flash this diagram again. So these were experiments with GeV, or the decay at rest, in many MEVs. And they were looking at, in this triangle, appearance of electron neutrinos in a muon neutrino source. Of course, you can do other experiments. If you assume there is a sterile neutrino that neutrinos can oscillate to, you can have disappearance of electron neutrinos now going into sterile, or also in muon neutrinos. And there is in particular a category of experiments at reactors, so at MEV type neutrinos and very, very short baselines that look at disappearance of electron neutrinos. That's going to be the next couple of slides. So there are several of them at the world, here also in Korea, Russia, in Europe, and also in the US. And they are basing their detectors very, very close to the reactor. The baseline has to be meters. So you can see here is a picture of the reactor containment building. Here is the reactor core. and the detectors are placed as close as possible to the reactor to get a short baseline. In this example here, it's on the side. Other experiments have their detectors on the bottom, depending on where they get access to from the operating reactors. They all use inverse beta decay as a detection mechanism where the antineutrinos come in, hit the protons, emit a positron and a neutron. Positron annihilates, makes a prompt signal, while the neutron scatters, thermalizes, and is then captured on gadolinium or on lithium, as in the case of the solid detector. So it gets the delayed signal, and by analyzing both, one can detect the antineutrinos the same way as we have done, or they had done earlier on the discovery of the neutrinos. So I'm just going to flash a few results. I'm not going to go through all the results in detail, just going to point out a few of the particularities. Here in the case of DANS, as also for the others, they are not basing all their measurements on an assumption that they know the antineutrino flux from the reactor, but they can change the baseline, and so they can really scan the oscillation pattern along the length and the flight length of the neutrinos. So DANS have put their detector on a lifting platform, and so they can scan at 3 locations, at 3 heights. They claim they're never going to ride while the detector is moving, but if I look at their faces, okay, we should ask them themselves. So they have all shown first results, again, in this delta m square sine squared to theta plane. You can see here are the allowed regions, these open areas here, and here the measurement with the exclusion. Some regions are excluded, some others are still compatible with the measurement. The same from the NEOS detector. You can see a fit to possible oscillations along in these energy distributions of the neutrino rates. And also here you can see the exclusion that they can see. The challenges in these experiments are typically anomalies seen, as we will see from the next talk on the reactor spectra, the understanding of the burn-up cycles, for example, samarium poisoning in the reactors, or also the size of the reactor core, which is sizable compared to the length they can scan their detectors. So NEOS will try to make a measurement, or will do, starting the end of this year, by just a single burn-up cycle, trying to get that systematic out of the equation. There is another set of experiments, also here I'm not going in detail, but I'll point out that they run at compact reactors with use highly enriched uranium-235, and so they get the burn-up cycle and also the size of the reactor diminished in their effects. I'm just putting the logos in big, so if you see results from these experiments that will ring a bell future, so that prospect, stereo, and solid, and they all showed first results in these planes of exclusion and compare, and you can see all three, they get close to the allowed region from previous experiments, but they will continue running to extend the sensitivity. So if we combine all of these results on these sterile neutrinos, again for the disappearance measurements, the appearance, and also results from disappearance of muons, you can see the results in these plots here. As far as the disappearance from electron neutrinos are concerned, there are still strong indications of allowed regions, in particular around this 1 eV square. It's close to or above or slightly below 3 sigma. If you look at electron muon appearance, also here from the LSND and the mini-boon experiments, although there are also some exclusions of experiments like Opera and Icarus earlier. But if we look at results as have been shown from the long baselines on the disappearance of muon neutrinos, these exclusions are pretty strong, and they cover pretty much the phase space of the appearance and disappearance from the EEC from the other experiments. So if we take this all together, there is a tension between the results here shown in red on the appearance result and the disappearance, in particular from the muon neutrinos here, which exclude this region, and this will have to be sorted out with more results in the future. You see the prospects on this. This is from another combination. You can see these preferred values here and here there is all the prospects from the short baseline or from this JNS square experiment, and also here from the reactor experiments, which will all cover these regions in the couple of years to come. Let me switch gears for the second half of the talk and talk about GeV neutrinos still on the short baseline, the same experiment here at Fermilab. Also others that can do the sterile neutrino searches. They also act as near detectors for the long baseline searches. And because they have a much shorter baseline, as said with the 1 over L square, they have high rates of neutrinos, so we can measure cross-sections. This is an image from a microboon shown by David on Thursday. The neutrino, of course, we can't see, so we have to base all these measurements from the the visible particles that we see in the final state after the interaction here. So it's pretty much like at the collider detector, where we don't really know the initial state event by event. On the gluons, also here, we have to base all the measurements on the final state particles that we see. But it's actually getting even a little worse. So while in the collider, we know we are in the deep inelastic scattering regime, here in the neutrinos, we are around a GeV. So as well for the neutrinos as for the antineutrinos, we have in a regime where there is a mix of quasi-elastic scatterings on the nucleons, resonances of the nucleons into deltas, and then a start of the DIS scattering. But here on the right, typical neutrino beam energies for experiments like T2K, the NOVA, Rosodun in the background here, and you can see they are all around this GeV region here. So it's you have to make some assumptions or disentangle the various interaction regimes to really understand the scatterings of neutrinos. And even more, it's not just the interaction on a single nucleon, but there is also a nucleus. These experiments need mass, so they are done on heavier nuclei. So in addition to the free nucleon scattering, there are initial states of the neutrons and protons inside the nucleus, Fermi motion. There are correlations of nucleons inside the nucleons that play a role and enhance the cross-sections. And on the produced particles, they scatter inside the nucleus, so you have final state interactions. And this all plays into the measurements of the cross-section, and all of this we need to disentangle from the final state particles that we actually see in the detectors. So this is not just for the cross-section measurements themselves. This is relevant for the, and crucial for also the long baseline neutrino oscillation measurements. I've put a plot here from an example from T2K, still with low statistics. You can see the non-oscillated, so if there were no oscillation spectra that they would see here with this peak. And of course, we know there are oscillations, so that's the spectrum they will actually measure in the FAR detector. Now, for this first order oscillation, this is not a problem. But now all the other measurements of CP violation and mass hierarchy are based on the measurements of the spectrum here of the oscillated neutrinos. And we need a very high level of precision to extract those physics quantities. Now, I've taken from a paper on the archive from a couple of years ago. You can see now the effect of some nuclear models here that are included in a generator. And you can see it doesn't only shift the height at one specific energy, it also shifts the interpretation of the energy, and that has a severe impact on the systematics and the understanding for neutrino oscillation measurements. And we remind we need precision level on the expectations to be able to do those measurements. What we actually measure is rates, so it's flux times cross-sections times some detector efficiency. And even if you do a near to far ratio measurement, with this being the oscillation probability, this is done in the true neutrino energy from the propagation. And as you already can see here, we don't know the true neutrino energy, so we have to assume all these nuclear physics models and the different interaction regimes to extrapolate to the neutrino energy back, and this is a difficulty, and so it is important to understand these cross-section measurements in the for neutrino experiments. So all these effects that I have said here, they all have got into the cross-section measurements, but it's not that we have one-to-one correspondence and we can sort them out by single measurements. They are all intricated. So every measurement we do has an effect on multiple, or if not all, of these effects, from the Fermi momentum to the multinucleon and also the final state interactions. So we like to talk about simple CCQE, quasi-elastic charge current interactions, and just a quasi-elastic part. And we select for this events, for example, which have no pions. So it's just a scattering on the nucleon. But this final state could also be due to a resonant production and a delta that decays in a pion, and the pion is reabsorbed in the nucleus, and so gets back to the final state. So it's not possible to do pure event selections on just quasi-elastic. We have to select final states, and on these final states, then see the effect on all the various nuclear models and the different interaction regimes. So what I will show next is some measurements based on such final states. There's one from T2K. Callum has shown on Friday. This is exactly such a measurement. Count the number of protons that are visible in the final state. And this is the cross-sections for 0 proton, 1 proton, and 2 proton, and then compared to a number of models, in particular these two P2H, which enhance the correlation of nucleons inside the nuclei. And you can see some of them then fit better. The plot here on the bottom shows the shift due to the fit to these models as opposed to the original expectation, and you can see some large deviations in this plot show that enhancing some of these nuclear model effects are really needed to fit the data. It's impossible to go through all the cross-section measurements. I just picked a few that I thought were interesting. So the second one is an example where the variables that are plotted are being studied. Here is the number of protons. This is close to what we do in collider physics, start to use missing ET in the neutrino world. Also here, because we don't know the initial longitudinal momentum, or we don't know the neutrino comes in straight, and so one looks at the momenta difference, or sum, in this case at the difference of the momenta of the visible particles, and uses those variables to plot the events. And you can see also here there is good sensitivity then in such variables to the various nuclear models which are fitted and tuned in these studies. Also here it appears that correlations among nuclei is something that needs to be added that are relevant. So other experiments which are targeted at such cross-section measurements like Minerva at Fermilab, sitting in front of the Minus near detector. So they have also a multitude of different targets in addition to be able to see the charged particles from the neutrinos, like a liquid helium. They have lead, iron, and water targets. You can see here an event of the muon produced from a muon neutrino, probably a neutron, and then ejects here visible through this proton interaction. And the game is same. I think I picked this slide. Heidi asked, can we model this? And that's exactly the question. And so we have a generator and then add these additional nuclear models, random phase approximations, or these correlated nucleons, try to fit the data, and you can see that compared to the original models, some decrease, some then enhance the models. We need to put these into the models to fit the data. The question is just exactly how. Minerva is also interesting because of the various variety of nuclei they have. You can see results here on carbon, on iron, on lead, and this of course changes the number of nucleons that we have inside and can give us additional insight into the nuclear physics. And also this is an interesting result where the tuning that was done on the neutrino side of the interaction was then applied to the antineutrinos. And you can see here, this is before, this is after the tuning from the neutrino on the antineutrino data, and this also seems to fit quite nicely. Some results from microboon, which is the first of the liquid argon TPCs at Fermilab, which have excellent tracking and calorimetry, also doing measurements of the multiplicity of the particles coming out at the vertex. Of course, with the liquid argon TPC and the good tracking, you can count the protons, muons, and pions inclusively. And also here, comparing it to a number of models. Also a measurement with the pi zeros emitted from charge current. You can see here the inclusive cross-section and the comparison to two models, or measurements inclusive on the charge current muon neutrino measurements as a function of the angle of the outgoing muon, which is also sensitive to a variety of models. So here the sensitivity will increase over the next years when the statistics is increased of these measurements. These are the first results that came out of this experiment. I just want to, in the last few minutes, cover, or 1 minute, a few more experiments that are relevant. We said for measuring cross-sections, one of the inputs is the flux. So it is important to be able to have a good knowledge on the flux. Shine Na61 is an experiment at CERN that does this. They also have replica targets from experiments like T2K, and their flux predictions, you can see how they were already able to, from 15 to about 10%. These are the uncertainties on the flux versus the energy, and they plan with such measurements to decrease the flux by another factor of 2. And of course, by already knowing the flux, we can then get better insight also on the cross-section. I have another example on trying to get a handle on the initial state, which is from KDAR, so kaon decays at rest. You can see here a spectrum of produced neutrino energy, and if you, these are the decaying flight. If you look at just the decays from kaons at rest, this is a sharp peak here, and so that is one example of using neutrinos that come from a known source and neutrinos with a known energy. So they're actually applied in mini-boon. And also here you can see that the measurements on the function of the energy transfer varies widely with the nuclear models used. Mini-boon has released the first result. The statistics is not that high. There's going to be more statistics with microboon and JSNS square too. In this, I'm just showing it. I think it's interesting to target where we know the energies of the neutrino such experiments. There is also one, Ken Long has shown a talk on Friday. If actually you talk about all these nuclear models and how they affect our oscillation measurements, and actually are there more a nuisance to these measurements, if you're interested in nuclear physics, of course having measurements that are sensitive to such nuclear effects, you could build up a whole program of nuclear physics, understanding the nucleon spin, and do precise determination of all these nuclear physics models. It just depends on how much money you want to throw at it. For example, NuStorm would be an option that delivers you a precise flux and a precise energy distribution of neutrino to do such studies. And one last example is what we have not been talking about up to now. This was all about electron neutrinos and muon neutrinos. Of course, there is also a tau neutrino, and Tomoko has shown a proposal to measure also the tau neutrino, where the cross-sections are largely unknown, a factor of 2 uncertainties, to bring them down to 10% in an experiment with emulsions, and study both the production through decays of d sub s, and then also the cross-section of tau neutrinos. And this could also then help in the total picture of neutrinos that we need for oscillation measurement. So to conclude, on the short baseline neutrino experiments, there are indications, strong also for sterile neutrinos, but there are also exclusion of sterile neutrinos. There is an ongoing program at short baselines and MeV and GeV scale neutrinos. They have implications also for the long baseline program, in particular to make precise neutrino measurements. And there is an effort to measure cross-sections. This is really crucial and surely needs more insight, in particular from nuclear physics. And of course, as always, new ideas and experiments are welcome. Thank you.
So we have a couple of minutes for questions.
Since you gave us this archive number 1803, what it says is that the disappearance measurement rule out the sterile neutrino interpretation of mini-boon and LSND at 4.7 sigma. I think that's something we should take seriously. What is your opinion?
Well, I said it's a tension, right? It's not measuring exactly the same thing. There are disappearance, and I said yes, they exclude it. But if you look at the appearance measurements from nu mu to nu e, or also in the disappearance of the electron neutrinos, the signals are still viable. I agree with you. This is something we do need to sort out.
What they do is they combine the disappearance from the nu e's and the disappearance from the nu mu's, which you can see are first order transitions, and put a constraint on the second order transition, which is the product. So I think this is fairly solid. And in addition, there's a qualitative thing. That is, the disappearance measurements are made with experiments with near and far detector and oscillation patterns like IceCube, while the appearance measurements are single experiments with no near detector. So there's a real, I think, it's beyond tension level, honestly.
It's your opinion. Thank you.
Okay, we have time for maybe one quick question. Benny?
Could you go to 4? If I understand you correctly, you're saying that the curve for the red curve, which is supposed to be 3+1 theory, if I'm not mistaken, it doesn't look like it matches the data.
Agreed? This is the best fit in a 3+1 model to the data. The chi-square isn't that great, indeed. And that's a fact.
Could that be a suggestion that there's some experimental issue involved?
Everyone has to interpret what they want. I think what one cannot refute is that there is an excess of events here, which is very significant. That it fits a sterile is another question. And that's where Microboon and the rest of the program at Fermilab will come in and hopefully sort this problem out.
Okay, I think we need to move on. Let's thank Michele for an interesting talk about some strange results. The next speaker is Ruben Saakian, who is going to cover the topic of non-accelerator-based experiments.
It's a pleasure to be here in this wonderful city and give an overview on non-accelerator neutrino experiments. Let me start with a disclaimer and apologies. This field has grown enormously in recent years thanks to its successes, and therefore I had to make some hard choices. So what I'm going to cover is the following, is the nuclear aspects of neutrinos from reactors. Oscillations have been covered in previous talks. Coherent neutrino scattering, neutrino mass from beta decay endpoint, and neutrino double beta decay. Unfortunately, I won't be able to cover the solid geoneutrinos and astrophysical and cosmological neutrinos, although we had a wonderful talk just before the lunch, which covered this topic. Neutrino magnetic moment, and undoubtedly many, many more. So for this, apologies. So we've heard already about two anomalies reported by all three reactor experiments looking at the longer baseline, Bay, Reno, and double shoes. One is the 5% shortfall in the absolute neutrino flux, and the other is the so-called 5 MeV bump. So you can see this here. So this is the picture from the Bay, and this is the global average, and you can see that there is a 5–6% difference between what the experiments measure and what the prediction is. 5 MeV bump is illustrated here. Again, you see that all three experiments see this high energy excess between 4 and 6 MeV. The question is, can nuclear physics account for this RAA? So one possible suggestion that at least partly nuclear physics can explain that is the observation of the discrepancy in the antineutrino flux evolution. If you compare, for example, the inverse beta decay yields per fission of uranium-235 and plutonium-239. Both experiments, Dea Bay and Reno, reported discrepancy for uranium-235 at the level of 3 sigma. So 5 MeV bump. So I'm actually here summarizing a very nice overview which Anna Hayes gave at Neutrino 2018. And the short summary of the 5 MeV bump is likely to have a standard nuclear physics explanation. There is an interesting discussion going on right now whether it could be attributed to uranium-238 and 235. And it's likely that upcoming experiments, especially those located next to highly enriched uranium reactors, can shed some light on this question. Now, another question is the absolute neutrino flux from the reactors. So this is a formula for the neutrino spectrum derived from beta decay. And it is shown in Anna Hayes' talk that if you play around with the Z effective and delta parameters in the nuclear physics, you can actually move the prediction of antineutrino flux by 4 or 5%. What I wanted to draw your attention to this new paper, which claims to actually, with a slightly different approach, solve both problems in one go, both the bump and the absolute neutrino flux. What the authors did there is to explicitly take into account the forbidden beta decay spectra for 29 most important isotopes. And as you can see here, so this is this author's prediction in red. You can see here that actually it removes part of the 5 MeV bump problem, but also the absolute antineutrino flux prediction. Right, so let me move now to coherent neutrino scattering. Although this is a non-accelerator neutrino physics, this particular measurement was done with accelerator. So coherent neutrino scattering is a standard model process which has not been observed despite having a high cross-section, orders of magnitude higher cross-section than inverse beta decay. The reason for that is because experimentally it's very challenging, because the recoil energy you have to observe are on the keV scale. So the first observation came from the spallation neutron source at Oak Ridge, which is actually incidentally the world's most intense at the moment pulse neutrino source, although it wasn't built for that. Sorry, go back. So the proton beam from that source hit the mercury target, and the neutrinos come from the stopped pions, from the decay of stopped pions and muons, so very well-defined flux. So the cesium iodide detector is the coherent collaboration has a number of different detectors, and the first observation was reported in cesium iodide. And you can see, so that this is, even without any sophisticated analysis with the BMON comparison, there is a clear observation of this standard model process for the first time. So this is a significant new result since the last ICHAP meeting. And note the size of the detector. It was observed only with 15 kilogram of cesium iodide. So that may be a very new, exciting era of so-called tabletop neutrino experiments. What happens next with the coherent neutrino scattering? So the attempts are now is to observe this at reactors, and probably the first experiment which is likely to see that is the KONOS. This is the experiment near the Brockdorf nuclear power plant in Germany, and it uses 4 1 kilogram germanium detectors located at 17 meters from the reactor core. They in fact started data taken in April 2018 and have some early indications that they start seeing this coherent neutrino scattering at the reactor. There is a very vibrant program of these small tabletop detectors which will be looking at the coherent neutrino scattering from other reactors, and I think it's a very, very interesting development in this area. All right, so let me turn now to neutrino mass observables. There are 3 main ways we can look at the neutrino mass. I will not cover cosmology except for saying that it looks at the sum of the neutrino mass eigenstates. The probably most model independent way, not probably, but definitely the most model independent way of looking at the neutrino mass is looking at the endpoint of a beta decay spectrum. So here, there are no models unless you don't believe in the energy conservation and momentum. There is a model independence. So the idea to look for it at the endpoint of the beta spectrum is probably as old as the neutrino itself, almost as old as the neutrino itself. Fermi, in his famous paper, actually pointed out that by analyzing the shape of the electron spectra near the endpoint, you can actually look at look for the neutrino mass. But the reality, of course, is much tougher because the number of events you will have in order to have this very good energy resolution is tiny. So the tritium beta decay using the so-called Mach-E filter technology leading the way at the moment. They have the most stringent upper bound on neutrino mass of 2 electron volt. And the current aim is to improve this by an order of magnitude. So this is a very exciting time for the Katrin experiment and for the whole community. So the Katrin is now in a running mode. So the idea of the experiment is in principle very simple, but the realization is incredibly challenging. So you need a very low density gas source, the tritium source in this particular case. Then you need to transport your electrons to a spectrometer, and spectrometer is basically an electrostatic filter which gets through only electrons higher than the potential you set. There was an inauguration. Many of you in this room, I'm sure, have been there. It happened straight after the neutrino conference in Heidelberg. And excitingly, the first tritium injection happened on the 18th of May this year. So what's happening here is that the injection was 1% of the nominal activity, and you can see that the all parameters are extremely stable, and the count rate absorbed, the spectrum basically absorbed in the experiment is exactly as expected. So how do we build on this success and push sensitivity to neutrino mass further? The limitations of the Mach-E filter technology are twofold. One is the spectrometer size, because the energy resolution required for the scales with the spectrometer size quadratically, but also the molecular physics uncertainties. You can see how having the uncertainty, theoretical uncertainty in molecular tritium wash out your sensitivity. So the concept of the Project H, which is aiming at tackling this problem, is in principle very simple, is to actually measure the cyclotron frequency of an electron in a magnetic field. And this is something we can measure very well. As one of laser co-inventors said, never measure anything but frequency. So this is basically what it is. You have a tritium inside a superconducting magnetic coil, so inside a magnetic field, and an array of antennas, which allows you to measure the power at different frequency. And you can see these diagrams which give you the energy of the electron. The electrons you're interested in is the highest energy electron is the lowest frequency over here, and the resolution which you can achieve with this is in principle very high. So the ambitious goal is to move eventually to atomic tritium to get rid of these molecular uncertainties. And you can see that in principle, it will allow us to close in to this 40, even below 40 millielectron volt sensitivity. And it means that we may be, if that's successful, that technology works, closing in on a guaranteed detection of neutrino mass. So a completely different approach are microcalorimeters. So the idea here is to embed the source inside the detector or make the source the detector itself. So in this case, for example, the most popular isotope for this currently is holmium-163. This is electron capture, not beta decaying isotopes. The idea is that you can actually measure everything inside the calorimeter. In case of atomic capture, you measure the X-rays energy electrons. There are two main approaches to do this. One is measuring the change in magnetization of a paramagnetic material, and the other is measuring the resistance of the superconducting transition. In both cases, these detectors exploit a very low specific heat capacity of certain crystals at temperature close to 0. All right, so let me now move to the neutrinoless double beta decay. And if you just want a punchline, then the short summary is that we haven't found it yet. Now, I'll skip through the big picture because Sergey will give a talk straight after me, and will do a much better job giving this. So I just wanted to give my humble experimentalist view on this decay. And when I look at the diagram, which we all know probably, is that this is nothing else but a creation of leptonic matter. And you can insert any new physics, any new lepton number violating physics inside this black box. So the message is we need to design experiments which are open-minded enough to search for any lepton number violating physics, regardless of the mechanism behind this process. The most popular scenario, of course, is the light-Majorana neutrino mass, and it very nicely connects us with the neutrino oscillations. So the rate of this decay, this is unfortunately a nuclear process, and the rate of this decay is proportional to the nuclear matrix element that we need to evaluate theoretically. This is a very hard job, and a lot of progress have been made in different nuclear groups, but the uncertainties are still there. So what you see in this plot is the nuclear matrix element calculations in different models, right, as a function of different nuclei, different double beta decay isotopes. There was recently a hotly debated topic of the GA. You can see that the possible quenching of GA in the nuclear matter can be quite damaging for the sensitivity of this process. So it's important to carry out all these different calculations, but it's equally important to provide some experimental input into these calculations. And it can come from the investigation of 2 neutrino double beta decay, but also charge exchange reactions and muon capture. So the 2 neutrino double beta decay actually have been observed for 12 nuclei. Those are the lifetimes. It's sobering actually sometimes to compare it with the age of the universe and how long this process are, how slow this process are, how difficult it is to detect them. Nevertheless, it has been observed for 12 nuclei. I list here not all 12 of them, but the most experimentally interesting. And as I said, they give an input into nuclear matrix element calculations. So this is a rather simplistic formula for sensitivity of double beta decay, but nevertheless quite instructive. It tells you that you need to have a lot of isotopes, with a good fraction of the isotope in question, a lot of material, and measure it for a long time, but also have a very low background. So the plot over here shows this sensitivity as a function of the exposure in kilogram years. This is a kind of equivalent of collider luminosity. And you can see that you benefit a lot from sitting in the background-free environment. It's a tough nut to crack. If you look at the event rates, which you expect for different scenarios, so this is the famous plot that shows you the effective neutrino mass as a function of the lightest neutrino mass eigenstate. So the plot, this is a plot straight from Andrea Giuliani, presented at Neutrino 2018. You can see that if you want to, for example, reach the bottom of the inverted ordering, then you need to have, even if you have tons of isotopes, where you're talking about a handful of counts, and sometimes even less than handful of counts. So the backgrounds are extremely important. So the observables are basically these two electrons emitted in the decay. For two neutrino, you have the continuum spectrum, and for the zero neutrino, you have a peak, of course, washed out by the energy resolution. There are two main approaches, and why the homogeneous detectors, typically source is equal to detector there, and heterogeneous detectors, in which source is not equal to the detector, and each have advantages and disadvantages. So it's a schematic plot of the historical progress. Double beta decay have been searched for many, many, many years, but a lot of progress have been made. And I think a lot of progress have been made due to the dedication, ingenuity, but importantly, diversity of the field. We collaborated and pushed each other at the same time. Lots of improvements have been made. And some of the experiments are now closing into zero background, which was assumed impossible only maybe 5, 10 years ago. So I'll very quickly flash you through several technologies. I will not have time to do justice to basically any of them. But talking about the zero background, let me mention Gerda experiment, which searches for double beta decay in germanium-76. So those are enriched germanium detector arrays operated in an active liquid argon veto. So you can see that the spectrum from phase 2 of Gerda is really extremely clean. They do a blind analysis, and you can see it seems to be a very narrow window, but the only reason why window is so narrow is because the resolution of the germanium detector is so good. It's a 3 keV. So when they open this, so they count a few events, but actually in the region of interest around 2 sigma, they don't have any background, right? So there is essentially zero background experiment, and this is a large-scale experiment already. So the next step of germanium detectors is legend, is basically merging the best of the Gerda and Majorana experiments. Majorana experiments is a germanium experiment in the States. And you can see that there is a phased approach is adopted. The Legend 200 will use the existing infrastructure at the Gran Sasso National Lab in Italy, where Gerda currently located, in order to improve the background by a factor of 5 roughly, and also to and reach this kind of sensitivity. And then the next step will be Legend 1000 with 1000 kilogram of germanium to reach the sensitivity of 10 to the 28 years. Importantly, and I think the community should come to that now, is that the sensitivity is presented not only as an exclusion, but also as a 3 sigma discovery potential, and you can see it in the plot on the right. So another technology I briefly wanted to mention are bolometers. I already talked about them in the context of the microcalorimeters. It's the very, very similar technology. So the pioneering experiment there is Cori, well, predecessors of Cori actually. So these are the 5 by 5 by 5 crystals arranged in 19 towers. rated again at 10 millikelvin. So again, you exploit this low heat capacity at superconducting transition. And this is the latest result released by Core, and they will continue taking data in Gran Sasso to reach the sensitivity of 10 to the 26 years. So here, I would like to just to very quickly flash. So one of the problems with the bolometers is the surface contamination, and the scintillating bolometers came to the rescue. The idea of scintillating barometers is to add another light detector over here in order to use the discrimination power, the fact that the alphas and the gammas look differently if you combine the signal from these two detectors. So there is a wide program which was discussed extensively at this conference and also at Neutrino, which way to take in order to get there. So one scintillating bolometers program I'd like to mention is Amore. So this has a clear Korean leadership, as you can see from the number of posters at this conference. It's a very interesting approach. It's this so-called metallic magnetic colorimeter approach. And in principle, if the background can be kept under control, this approach can give you a very good background suppression and a very, very competitive sensitivity with a relatively modest amount of isotopes. Of course, getting to those background is very hard. Right, so I won't have time to go through all these experiments. I just will flash the names and main technologies for you in case you are interested and want to come back and look at it. So XO200 and NEXO look at the liquid argon. It's a liquid argon TPC experiments. Now, the large liquid scintillator detectors exploit the idea of dissolving double BTK isotope in a very large and very pure big scintillator. So this Kamlan Zen currently holds actually the most stringent limit on the neutrino mass. And the Snow Plus, using slightly different technology, instead of containing the isotope xenon in case of Kamlan inside the balloon, it puts it in the entire detector. All right, so finally, very quickly, I want to mention that there are also technologies in which full final states of the particles are reconstructed, and they can be very important in the event of a discovery to probe the underlying mechanisms through the correlations. So in the final couple of slides, I would like to look into the future sensitivity. There were a couple of papers which try to look globally at what the future experiments can achieve. So one particular paper is shown here, and it looks actually very interesting. So what is shown here is a 3 sigma discovery probability, right, given all the constraints we know as a function of lifetime, with a reasonable lifetime of 5 years or so. And you see in the case of the inverted ordering, right, so the discovery probability is very close to 100%. But even in the case of the normal hierarchy, if there is no mechanism which drives this lightest neutrino mass to 0, there is actually 50% chance of making a discovery, given the current knowledge of the mass of neutrino mass parameters. So couple of comments I wanted to make. It will be very difficult, of course, to go below the inverted hierarchy. It will require novel ideas, perhaps completely radically novel ideas, and undoubtedly consolidation of worldwide effort. But as I mentioned at the beginning, the zero new double BTDK is a quest for lepton number violation. And the plot above is a good metric, but should be understood in a much wider context. The observation of zero new double beta decay will mean that the neutrino Majorana, this is a so-called Schechter-Wallich theorem, but it's not a given that the neutrino mass, the Majorana neutrino mass, is necessarily the driving mechanism for this lepton number violating process. So the normal ordering, even if it is confirmed, cannot be a reason to stop searching for lepton number violation. So with this, I conclude. This field has made striking progress even since IHF 2016. We have first tritium events in Katrin, and the idea is how to actually reach the lower bound on the neutrino mass. We have zero background, so the zero background 100 kilogram scale experiments become reality, and the community is ready to move to ton scale experiments with some reasonable and reliable extrapolations. We have a first observation of coherent neutrino scattering, and it opens new physics and technological opportunities, and neutrinos become a tool to understand the nuclear reactors. So it was impossible to do justice to such a vibrant field in a little bit more than 25 minutes, and apologies for having to omit many of the ideas, especially if those happen to be your preferred ideas. Thank you very much.
The next speaker will be Sergei Petkov, who will cover aspects of neutrino theory.
Okay. It's a great pleasure to talk about neutrinos at this really very representative meeting in a beautiful part of the world. So my talk will be devoted to some aspects of neutrino theory. I mean, it's a 25 plus 5 minute talk, and it's impossible to cover all aspects. So let me begin with a statement, namely, understanding the origin of the pattern of neutrino mixing and of neutrino mass square differences which emerged from the data recently is one of the most challenging problems in neutrino physics. And my talk will be mostly devoted to this problem. It is part of the more fundamental problem in particle physics of understanding the origin of the pattern of quark masses and mixing, of charged lepton and neutrino masses, and of neutrino mixing. Now, of course, in neutrino physics, of fundamental importance is also the determination of the status of lepton charge conservation and the nature, Dirac-Majorana of massive neutrinos, the determination of the status of CP symmetry in the lepton sector, determination of the type of spectrum neutrino masses obey, which can be of normal or inverted ordering, and determination of the absolute neutrino mass scale. And these problems have been discussed amply at this conference and are the focus of a comprehensive research program in neutrino physics which extends beyond 2030. Now, what is the problem? We know from the data that neutrinos have mass and mix. That means that the states, the fields of the left-handed neutrinos which enter the weak interaction Lagrangian are actually linear combinations of fields of neutrinos which have definite but different masses. U here is the Pontecorvo-Maki-Nakagawa-Sekata neutrino mixing matrix, which is the analog of the quark mixing matrix. We know also from data that at least 3 of the massive neutrinos must be light, must have masses smaller than about 1 electron volt. That means that the neutrino masses, I mean, neutrinos have masses which are much, much smaller than the masses of charged leptons and quarks. This enormous disparity between the masses of neutrinos and the masses of charged leptons and quarks suggests that the existence of neutrino masses is related to the existence of new mass scale in particle physics, that is, new physics beyond that predicted by the standard theory. Now, this new physics can have different manifestations. It can manifest itself in the existence of more than 3 massive neutrinos, in the observed pattern of neutrino mixing, and in the values of CP violating phases in the neutrino mixing matrix, in the Majorana nature of massive neutrinos, in the existence of new particles at the TV scale. This could be heavy Majorana neutrinos, doubly charged scalars, and so on. In the existence of new non-standard neutrino interactions, and in the existence of charged lepton flavor violating processes which proceed at rates which are close to the existing stringent upper limits. Now, all this has been discussed, of course, at this conference. we can have more than 3 massive states, for example, if there exist right-handed neutrinos and they mix with the active left-handed neutrinos through Dirac and Majorana mass terms. Now, in what concerns the masses of these states, there are several possibilities. Some of them can have masses at the EV scale, and in that case, we have active sterile neutrino oscillations. And as we heard at this conference, there are indications for the existence of such oscillations. However, the overall picture is incoherent and rather confusing. The good news is that there are a large number of experiments which are either taking data or are in preparation, which are going to test this hypothesis, and I think that within the next 3-4 years we will know whether active sterile neutrino oscillations actually take place. The second possibility is that some of these states have masses in the range of 1 GeV to 1 TeV, and this would correspond to low-scale seesaw models. In this case, these states may be accessible to low-energy neutrino, low-energy experiments, and this also has been widely discussed in this conference, how to search for such states. Finally, these additional states can have masses close to the GUT scale, and this would correspond to the GUT seesaw models. Now, in the case of reference 3 neutrino mixing scheme, the PMNS matrix is a 3x3 unitary matrix, and it can be parameterized by 3 angles, and depending on whether the massive neutrinos are Dirac or Majorana particles, by 1 Dirac and 2 Majorana CP violating phases. And in the standard parameterization, this matrix has this form, where V contains the Dirac CP violating phase, while P contains the 2 Majorana physical phases. Now, the enormous amount of neutrino oscillation data accumulated over very long period of studies allows us to determine the parameters which drive the solo neutrino oscillation, delta m squared 2, 1, the angle theta 1, 2, the dominant oscillations of atmospheric mu neutrinos and antineutrinos, delta m squared 3, 1, and the angle theta 2, 3, and the angle theta 1, 3 that drives the oscillations observed in the Diabay, Renault, and double show experiments with remarkable precision. This is a table which summarizes this knowledge. This shows the results of one of the latest analyses of the global neutrino oscillation data. Few comments are in order. First of all, the angle theta 1, 2, we know from data, is definitely smaller than pi over 4. Actually, the best fit value is about 33 degrees, and pi over 4 is ruled out at very high confidence level. The angle theta 1, 3 is about 0.15. Theta 2, 3, the best fit value is a little bit larger than pi over 4. However, pi over 4 is within 1.5 sigma from the best fit value. Now, in what concerns delta, we see that the data, the best fit value of delta is close to 3 pi over 2. And at 3 sigma, actually, delta is supposed to lie roughly in the interval pi to 2 pi. And these are very impressive results. Now, in what concerns the phase delta, it can cause, as you know, most of you know, CP violation affects neutrino oscillations, the magnitude of which is controlled by the rephasing invariant, JCP factor, which in the standard parameterization has this form. And the only not well-known, well-determined parameter here is just sine delta. If we use the indication for delta being 3 pi over 2 and the values of the mixing angles as determined by the oscillation data, we find that the JCP factor in the lepton sector in magnitude is by 3 orders of magnitude larger than the JCP factor in the quark sector. It's very difficult to get information about the Majorana phases because the flavor neutrino oscillation probabilities are not sensitive to these phases. These phases play a very important role in processes in which Majorana nature of massive neutrinos appears. And these are processes in which the total lepton charge changes by 2 units. One example is neutrinoless double beta decay. Now, our interest in this, in the Dirac and Majorana phases of the PMNS matrix is also stimulated by very intriguing and appealing possibility that these phases provide the CP violation necessary for the generation of the baryon asymmetry of the universe. One comment about the Dirac phase delta. The CP conserving values of delta 0 and pi are disfavored by the current data at 2.5 and 3 sigma, depending on whether the spectrum is normal ordering or inverted ordering, and at 1.7 and 3.3 sigma, while the CP violating value pi over 2 is really ruled out by the current data. Now, this is one-dimensional projections of the results of this global analysis. And from these projections also follows that the spectrum with inverted ordering is actually disfavored at about 3.1 sigma. Now, can we understand these numerical values? We have a very good qualitative understanding of why neutrino masses are much smaller than the masses of charged leptons and quarks through the seesaw and the radiative mechanism of neutrino mass generation. A very attractive feature of the seesaw mechanism is that through leptogenesis theory, it establishes a link between the neutrino mass generation and the generation of the baryon asymmetry of the universe. Now, we have 3 types of seesaw scenarios, and all of them require the presence of new degrees of freedom. In type 1, these are the right-handed Majorana neutrinos. In type 2, this is a triplet of doubly charged, singly charged, and neutral Higgs field. And in type 3, this is a triplet of fermion fields. The new scale, the scale of new physics, is determined by the masses of these new particles. In all these cases, the massive neutrinos are Majorana particles, and all these 3 types of seesaw mechanisms have TV scale versions, which predict rather rich phenomenology at low energy. This is a schematic view of the diagram which generates the Majorana mass for the left-handed flavor neutrinos in type 1 seesaw. It's a interplay between the Dirac mass generated by SU2 plus U1 invariant couplings, neutrino Yukawa couplings, after the spontaneous symmetry breaking, and the heavy Majorana mass term for the right-handed neutrinos. Now, if we use reasonable values for the Yukawa couplings of the order of 10 to the minus 2, and we want to reproduce the values of neutrino masses of the order of 0.1, we get that the heavy Majorana neutrinos have to have masses at the range of 10 to the 10 GeV cut scale. Now we have a similar situation in type seesaw, where this states the triplet has to have mass close to the Guth scale, and also in type 3 seesaw. Now, in the formalism of effective operators, the Majorana mass that is generated by all these 3 mechanisms actually is due to one operator, the Weinberg dimension 5 operator, which looks like that. Now, radiative generation of neutrino masses. The generic features is that loop suppression helps explaining the smallness of neutrino masses. New particles need not be super heavy, can be at the TV scale. Models at the TV scale are testable. There is no need to introduce right-handed neutrinos in some of the models. And typically, these models include extended scalar sector. I have 2 examples, one in which the standard model, to the standard model, one adds doubly charged and singly charged scalar fields, which carry non-zero weak hypercharges, but are SU2 singlets. These fields also carry 2 units of lepton charge, and their triple coupling actually violates the lepton charge conservation. Neutrino masses are generated at 2 loop level. The massive neutrinos are Majorana particles. The additional degrees of freedom can have masses at the TV scale, and we have rich possibility for very rich phenomenology at low energies. The second example is generation of neutrino masses at 1 loop level through the presence of right-handed neutrinos which have a Majorana mass term and a doublet of Higgs fields, which, however, due to the additional Z2 symmetry cannot develop a non-zero vacuum expectation value. Also, in this case, the neutrinos that are generated on Majorana fermions. The additional degrees of freedom can have masses at the TV scale. In this model, we have a candidate for dark matter, and there is also very rich phenomenology, low energy phenomenology, in case the additional degrees of freedom indeed are at the TV scale. Now, neutrino masses can be generated also at high order, as high order corrections, by the presence of non-renormalizable operators, and that has been studied extensively in the literature. But there are two operators that are listed here, which under UV completion require the introduction of leptoquarks, which have quantum numbers, which are also well-known candidates to explain the flavor anomalies, the indication for breaking of lepton universality in B meson decays. Now, this is all very nice, but it doesn't give us a quantitative understanding of the pattern of neutrino mixing, which we aim to achieve. So there are two schemes that aim also to do that, but they do not quite succeed in doing it, and therefore I'm not going to discuss them, and I will go just to the scheme that at least tries and has some success in doing it. Now, I believe, and I'm not alone in holding this view, that with the observed pattern of neutrino mixing, nature is sending us a message. And the message is encoded in the values of the neutrino mixing angles, leptonic CP violation phases, and the neutrino masses. We don't know, of course, we are not sure what is the precise content of this message at present. However, on the basis of the existing ideas about the origin of the pattern of neutrino mixing, I believe, and I am not alone, that the message, if expressed by one word, would mean symmetry. Now, what kind of symmetry? Actually, the peculiarity of the pattern of neutrino mixing is that we have two large mixing angles and one small mixing angles. And this is non-trivial to explain theoretically. And this observed pattern can most naturally be explained by extending the standard model with a flavor symmetry corresponding to a non-abelian discrete finite group GF. What kind of groups are at work here? This is A4, which is a group of even permutation of four objects. T prime, the double covering of A4. S4, group of permutations of 4 objects. A5, group of even permutations of 5 objects. And dihedral groups, D10, D12, and other. Why this approach seems attractive? Now, if you look at the values of neutrino mixing angles, it turns out that they differ from the values that can be obtained on the basis of non-abelian discrete symmetries by subleading perturbative corrections. Theta 1, 2 differs from the tri-bimaximal mixing value by 0.02. Theta 1, 3 differs from 0 by 0.15, and theta 2, 3 deviates from pi/4 by 0.1. Now, this approach also seems extremely natural in view of the fact that the PMNS matrix is a product of two pieces. One coming from the diagonalization of the neutrino mass term, and second coming from the diagonalization of the charged lepton mass term. Now, in this approach, it is natural to assume that one of these pieces actually has a symmetry form, for example, that coming from the diagonalization of the neutrino mass term, while the second provides the necessary subleading perturbative corrections, bringing the symmetry values of the neutrino mixing angles to be compatible with the observed one. Popular symmetry forms that are discussed in this approach to neutrino mixing are tri-bimaximal mixing, bimaximal mixing, the form which results from conservation of a non-standard lepton charge L prime, which is equal to LE minus L mu minus L tau, which augmented by mu tau symmetry corresponds to bimaximal mixing. The two golden ratio forms and hexagonal form. Now, the tri-bimaximal mixing can be obtained from A4, T prime, S4, bimaximal from S4, Group A5 gives golden ratio A, and the dihedral groups give golden ratio B and hexagonal mixing. For all these symmetry forms considered, theta 1,3 is 0 and has to be corrected. Theta 2,3 is pi over 4, and if pi over 4 deviates significantly from, if theta 2,3 deviates significantly from pi over 4, has to be corrected. These forms differ by the value of the angle theta 1, 2 nu, which for the fine forms in sine squared theta 1, 2 has these values, 1/3, 0.5, 0.276, and so on. Now, these symmetries are also symmetries of geometrical objects. A4 is the symmetry of regular tetrahedron. S4 is the symmetry of the cube. Dn is the symmetry of the regular polygon with n sides. And A5 is the symmetry of icosahedron. How this works? I mean, let me give you an example of predictions that one gets in this approach. So suppose that the part of the PMNS matrix coming from the neutrino sector has one of the symmetry forms, and the correcting part coming from the charged lepton sector involves a rotation in the 1, 2 plane, or a combination of rotations in 1, 2, or 2, 3 planes. Now, in that case, it is easy to show that the cos delta actually satisfies a sum rule by which it is expressed in terms of the 3 mixing angles and the parameter theta 1, 2 nu, which depends on the underlying symmetry form of the PMNS matrix. Now, in the minimal case, there is also a correlation between the angle theta 2, 3 and the angle theta 1, 3. How these predictions look like for cos delta? If we use as input the data, the best fit values of the mixing angles as determined experimentally, and, for example, the prospective precision in the measurement of sine squared theta 1, 2, sine squared theta 1, 3, and sine squared theta 2, 3. This is shown on the next slide. This corresponds to tribimaximal mixing, golden ratio B, golden ratio A, and hexagonal mixing. Can you distinguish these cases experimentally? This we have tried by analyzing the prospective data from Dune and T2HK. And the result is that you can distinguish golden ratio B from hexagonal mixing at more than 3 sigma, golden ratio A from golden ratio B at more than 2 sigma, tribal maximal mixing from hexagonal mixing at 3 sigma, and so on. And as we heard yesterday, from T2A, if one adds the T2HKK prospective data, one would have even better sensitivity. Now, this slide shows predictions which can be obtained in other models based on discrete symmetries. So one of the most characteristic aspects of this approach to the neutrino mixing is the predictions either of the values of the neutrino mixing angles, or the predictions of existence of correlations between the values of 2 neutrino mixing angles, and the existence of correlation between the value of the Dirac phase and the 3 neutrino mixing angles, which depends on the underlying symmetry of the PMNS matrix. Now, this tells you that actually the measurement of the Dirac phase in the PMNS mixing matrix, together with the improvement on the precision of the mixing angles, theta 1, 2, theta 1, 3, and theta 2, 3, can provide unique information about the possible existence of new fundamental symmetry in the lepton sector. What our experimentalist colleagues should aim at, these are the precisions on theta 1, 2, theta 1, 3, theta 2, 3 that are planned to be achieved in Juno, Diabase, and T2HK and Dune, and that will be sufficient. It is very desirable to reach 1 sigma precision in the measurement of delta at the level of 10 degrees for testing this approach. One of the most attractive features of this approach is that it is testable and falsifiable. Now, leptogenesis. For leptogenesis, I don't have time. And indeed, I mean, with 25 minutes plus 5, it's impossible to discuss the theory of neutrino masses and mixing, and also leptogenesis. Leptogenesis required a separate, actually, probably a separate discussion. I guess that I don't have, my time is over, as I assume.
Almost.
Maybe I can say just 2 words. For me, the most important question in leptogenesis is whether the CP violation necessary for the generation of the baryon asymmetry indeed can be provided by the low energy phases which sit in the PMNS matrix. That would imply that by measuring, if this is the case, by measuring these phases, I mean, we are doing something fundamental, really, which is relevant for even in an indirect way, even for our existence. And the answer to this is possible in the sense that, indeed, the phases in the PMNS matrix can provide the CP violation necessary for the baryon asymmetry of the universe. And there is even a necessary condition for the success of successfully reproducing the baryon asymmetry if all the asymmetry is due to the Dirac phase in the PMNS matrix. And this condition is somewhere in the slides. I will try to get it. Here it is. So the necessary condition, which is obtained, it's a necessary condition and not sufficient. That should be clear. Reads like that. Sine theta 1, 3 sine delta bigger than 0.11. And this is beautifully compatible with the measured value of theta 1, 3 and the indication that delta is close to 3 pi over 2. Now, of course, I should explain how this condition is obtained. It is obtained under the conditions of hierarchical heavy Majorana neutrino masses and under the condition that leptogenesis take place in the flavor regime, which means that the scale at which the baryon asymmetry is generated is below 10 to the 12 GeV. Now, these conditions do not seem extremely artificial. Actually, they seem rather natural. So with this, I will conclude. Let me go to the conclusions. Understanding the origin of the pattern of neutrino mixing and of neutrino mass square differences that emerge from the neutrino oscillation data in the recent years is one of the most challenging problems in neutrino physics. The observed pattern of neutrino mixing can be due to a new basic symmetry of particle interactions leading to an approximate symmetry form of the PMNS matrix. The most important testable consequence of the symmetry approach to understanding the pattern of neutrino mixing is the correlation between the values of some of the neutrino mixing angles and or the value of the delta and the values of neutrino mixing angles. The second correlation depends on the underlying approximate symmetry form of the PMNS matrix. This means that the measurement of the Dirac phase delta in the PMNS matrix together with an improvement of the precision of the mixing angles theta 1, 2, theta 1, 3, and theta 2, 3 can provide unique information about the possible existence of new fundamental symmetry in the lepton sector. In view of this, of course, understanding the status of CP symmetry in the lepton sector is of fundamental importance. The seesaw mechanism provides a link between the neutrino mass generation and the baryon asymmetry of the universe. All the CP violating phases in the PMNS matrix can be leptogenesis CP violating parameters. Low energy leptonic CP violation can be directly related to the existence of the baryon asymmetry of the universe. These results underline further the importance of the experimental studies of Dirac and searches for Majorana leptonic CP violation at low energies. To our experimental colleagues who do these experiments, I would like to say that you're not measuring just another parameter of minimal extension of the standard theory with massive neutrinos. With measuring the Dirac phase delta and with high precision measurements of the neutrino mixing angles, we are probing something fundamental about the pattern of neutrino mixing which emerge from the data. Thank you.
So open this talk for questions.
Now, I couldn't understand, and maybe it's up there, what did you do with the 3 plus 1, whether we do or do not have, you know, a 3 plus 1 or more situation? Do you just ignore that in this table, or is that in this table?
No, if you listen carefully, I said that I will restrict myself to the case of 3 neutrino mixing.
So you just ignore that,
right.
All that, any data that suggests otherwise, you drop it. Okay.
Other questions? Over here.
3 plus 1 is not proven. Huh? It takes time to prove it that it's correct. And it's not clear that it will be correct, actually.
We can't hear you. We can't hear you.
Ah, yeah.
My question is related to leptogenesis. You talk about the necessary condition. What about the sufficient ones?
Sufficient
conditions.
There is no sufficient condition because you can have many mechanisms, I mean, many different mechanisms which
but maybe some bound. There is no bound.
No. Can generate baryon asymmetry of the universe. But if you have a framework in which you have leptogenesis and you generate the baryon asymmetry through CP violation from the neutrino mixing matrix. By framework, I mean renormalizable theory, complete theory, and you test all possible aspects, all possible predictions of this theory at low energies, and they turn out to be correct. I mean, the theory passes the test. It's very likely that this is what actually generates also the baryon asymmetry. There is no way to test the hypothesis of leptogenesis at the gut scale directly. You can only do it within a framework and indirectly. For example, if neutrinoless double beta decay experiments discover that neutrinos are Majorana particles, that will be a right step in that direction. Very important one.
Okay, we have time for one quick question, perhaps. All right, if not, let's thank Sergey and all the speakers in this session.